Hi class, it's Bill Berry here, and we are finishing up our series on trees. We've had a couple of videos that set up the basics, talked about the concepts and the terminology, talked about x equals change x, which is important in our recursive methods, and then we had some videos on the methods themselves. So now we're talking about a couple of the more challenging methods. We're not going to look at quite as much code this time, but definitely we'll cover some methods that you're probably curious about. So let's get started. We'll finish those up, I think, in probably a single video. So the algorithms that we're going to talk about, again, a little bit more challenging. Let's first look at display versus get. We have a display method, and remember that any of these methods are simpler if they don't have to deal with data being returned upstream. That's one of the things that gets a little bit difficult with recursion, is figuring out how to return the data so that the previous iteration of the recursive call can consume it. So you'll want to practice not just with methods that don't have returns like display, but you'll want to practice with things that do require returns, because you'll have to think a little bit differently about them. So let us jump over and look specifically at that code. Again, the magic here is in the returns. So let's go look at the get data list. And of course, we're going to start with a simple one that is a client-facing front end that's public. And notice it's going to return a string, of course. And we're going to start by calling the recursive method and calling it using the root, of course, right? So none of that is a big deal. Now, this is just a little like workaround for fence posting, where I'm going to have an extra comma at the end because I'm not being careful. I'm just sort of throwing on a comma every time I add data. So I got to go take the last comma off to be a little bit nicer, and then I'm going to return that. So that's pretty easy. But now how about the recursive method down here? Of course, we have a start node. That's going to be kind of traditional and typical in these methods, necessary. And our base case is going to be that if we run out of road, right, if we end up with pointing to a node that is empty, then of course, if it's null, we return. Notice, since it's a string, we're going to just return an empty string. There's nothing to add. We have nothing new to add, so we're just going to simply return an empty string. Otherwise, if it's not empty, I'm going to create a local string. Now what we're trying to avoid here is to create a global. We could have created a global and used it here, but is it necessary? No, we don't have to do that to make this thing work. So let's not. So I'm going to create a new string, make it empty, and then I'm going to append to that string three successive things. First is I've got to go to the left. We're going to do an in-order traversal, so I need to go to the left. So I say, hey, I tack on to whatever this string is at this moment. I'm going to tack on the output from my left child's recursive call to get data list. So I call get data list, pass the left child, and off it spins. Then once that comes back, and remember that's not one call, that can be a lot for a tree, then handle me in order traversal, right? Do my left child, then do me, then do my right child. So then I take my start node that implies the toString, right? Start node's got a toString method, so I'm returning the toString result of me, of my data, and then I tack on my output separator, which in this case is a comma and a space, and then I tack on, in addition, the whatever data came back from the right node, recursive call to get data list using right node, right? The start node right child. And then I return that. So each one of these things returns its own string. So it's going to work its way down the list to the left. Eventually it's going to create and start returning little bits of that string. Those are all going to end up here. Then we're going to tack on ourselves and then move to the right, and all of that is going to be returned up and up and upstream, so that the calls that are higher up in the tree can then tack on their stuff. So again, these are one of these methods that takes a little bit to get your brain wrapped around how that returning works. So if you want to really understand it, spend some time in the debugger, write this kind of thing. Spend some time in the debugger and watch what those things are. Put a breakpoint here and watch every time it's about to return something, see what info is at that moment, and then you'll be able to return by stepping into, you'll be able to, or maybe step depending on which direction you're going. You probably want to step into. You're gonna go and see how that information is being consumed. So watch your local variables and watch how the calls are being unwound and how this is all working. So that's the magic behind these methods that require returns. Okay, so that's one. Let us now talk about delete, because we've sort of skipped over that. In all of our other data structures, we talk a lot about add, edit, delete. You know, what can we do here? But here we need to be able to delete. We're not going to write the code for this. It's a little bit complex, but you could certainly find it on the internet. But let's talk about the ideas here. The reason that this is complex is because you now have three different cases. It's not like a linked list where if you're using dummy nodes, you don't even care. Your code is identical for all cases. But even at worst, if you don't have dummy nodes, you just have the front to talk about. But when you're talking about a tree, you've got three different cases. You treat it differently. You write slightly different code if your node is a leaf node. If it has no children, then deleting it is pretty simple. If it has only one child, then there's another method, and if it has more than one child, then we have to think of it differently. So let's look at each of those cases, and I think you can intuit the code for this, but if not, again, go find some code on the internet and grab it, and you'll see that this is exactly what they're implementing. The first is an easy case. If your node that you're deleting has no children, just sever the tie. So in this case, if I'm deleting the 16, or if I'm deleting the 18, or even the 24, it's very easy. They have no children. All you have to do is set this reference to null. Take its parent's reference and set it to null, and that then just severs that tie. Off it goes. Garbage collector snatches it away, and away it's gone. So deleting leaf nodes turns out to be super easy. You just delete them, right? You just set the parent's reference to null, and that's easy as can be. So that's case number one. Now, your delete method is going to have all these three. You're going to have cases, right? Three sets of code that are going to deal with this with if statements. So if statement number one, if no children, then here you go. Case number two, well, in this case, yeah, the 16 goes away, so the animation just shows, hey, the 16's gone. Case number two, you have one child. So if, for instance, you are trying to delete the node here that has 17 in it, notice it only has one child. We don't care that there's more down here, but it only has one child, not two. So this is a one-child case. So what do you have to do with this? Well, it turns out that because of the unique properties of a binary search tree, it's pretty easy. What you really need to do is just get rid of this and make this reference sort of point around where that was. In fact, if you simply make this reference here point down to the child of 17, you've accomplished your task, and it doesn't disturb the properties of the binary search tree. So in that case, all you have to do is map around that, right? Set your reference from its parent to its child. So that's pretty straightforward. So what happens here is the 15 just comes up and takes the place of the 17, and whatever it had going on just comes along for the ride, whether it had one child, two children, no children, whatever. It goes along for the ride. So deleting something, a node with one child, isn't too hard either. We're just going to map around. So that's case number two. Two children, though, things get more complex. The first thing we have to do is find a successor, because with the two children you sort of got more entanglements. You've got to find another node that is a good candidate to take the place of this one. So the way that it typically works is you first turn right and then keep going left all the way down. So start like you're going down the right subtree, but then immediately turn left and go as far down as you can. Alternately, you could take a left and immediately take a right and go as far as you can. Either however you want to do that, right? But typically you got to find a successor, and that is going to be the closest value to what your value is, right? If you think about it, draw yourself a tree and look, that's the that is going to be the node with the closest value to you of anything in your subtree. Then don't work with nodes. Here's an interesting piece. Don't work with the nodes and try to move the nodes around. Just work with data. Copy their data portion, the successor's data portion, into your data portion, your being the one that you're deleting. Right? So find the successor, copy its data into the node that you're deleting, and then recursively call delete on the successor, because the successor might have no children, one child, or I don't think it can have two, right? I don't think it can have two, but it might have a child. So in this case, you want to recursively call delete because it might need some extra work too, right? It might need work. So that is the method with two children. So let's look at an example where we're trying to delete 12. So what is our best bet? What is our closest successor, right? We either are going to take their advice that we talked about here, which is take the right subtree, but then keep turning left all the way down till you run out of road. And here's where we run out of road, right? So 19 is our successor. We're going to copy 19 into this node's data, replacing the 12, and then we're going to call delete on this recursively with this as the start node, and therefore since it has no children it can be deleted directly and you have no worries. So 19 goes away and the tree is left with 19 here, and everything else doesn't have to be shifted. Everything else worked pretty good. Okay, so that's one example. Now let's look at another where we're going to have two, well, let's say we're deleting this. It seems like a more complicated scenario. It's really not that bad. So what happens here if you are trying to delete 40? Where's your successor? Again, we're going to turn right and then keep turning left and go all the way till we run out of road, and that's 50, right? Can't go left anymore. So 50 is going to be our successor. So we know we're going to copy the 50 up to here. This is going to become 50. And then we're going to recursively call delete on this with this as the start node, and therefore this has one child. So what happens here? With one child, it has to map around that, so it's going to take the left node of this one's parent and it's going to point it to this thing, sort of mapping around the node that's going to be deleted. So then the 55 is going to become this child on the left of 60. Does that make sense? So everything else applies. The recursive calls to delete don't change any of the rules. It just says, hey, when you're doing this, you sort of have to do this cascading work to make sure that you've cleaned up anything downstream. Once you've copied over that data, you've got to go clean up anything that remains, and that recursive call to delete is the magic. So that's how you do delete. You can imagine the code for this. It is a little more complicated because you've got to pay attention to parent nodes and things like that. So the code is a little bit more interesting, but certainly you can find it and look at it, but it will implement these ideas, and I think they make sense once you start taking a look at them. All right, so I do want to pause this video here because I don't want this to get too long, and we'll do one more thing when we come back, and that's that we'll talk about rebalancing. So I'll stop the video here and come back to the next one, and that'll be our last topic, I believe, on trees. Thanks for watching this video.